So sometimes you're explicitly asked to change the order of integration for an integral, but usually in practice what happens is the integral is presented in a way, or you come across it in the field in a way that's just not optimal for evaluating. So in this kind of a situation, you want to decode the bounds of integration to determine the domain. So in other words, you look at the bounds of the integral and figure out, okay, what's the region we're looking at? And then you just have to, from scratch, set this up in the other order using a careful consideration of that domain. And what that amounts to right here in practice is you want to use a sketch. So this first part is basically where you are making a sketch, and then in the second one part you set it up the other way. So let's look at an example. Suppose that you were given the integral from 0 to 2 y squared to 4 of y cosine x squared dx dy. All right, so now if you got such an integral and you started to just try and integrate it, then you would look at this thing and say, okay, let's see. So integrating with respect to x, y is a constant. So this is from 0 to 2 y integral from y squared to 4 cosine of x squared dx integrated dy. And after a moment's notice, or perhaps a brief glance through a table of integrals, you'll realize that when you go to integrate cosine of x squared, you're absolutely doomed. There is no way to do that. You're dead. That function has no elementary antiderivatives, so you're just not going to even get off the ground. Okay, doom. All right, so that tells you that you must interchange. It's impossible to integrate it the way it's currently given to you. Okay, so then we focus our attention on just the bounds right here and try and figure out, okay, based on that, what is the region? So we have to decode it. Okay, so let's see. So I'm gonna just start with some axes here and see what we got. And so I look at this and I interpret and I remember, okay, so this bottom curve right here, this is x equals y squared. So what does the curve x equals y squared look like? It looks like a parabola that opens around the x-axis, like that. Okay, so here's x equals y squared. And then I look at this one here, this 4, and again, since we're doing a dx integration first, that's telling you that this really means x equals 4. So then I go, okay, so 1, 2, 3, 4 out to here, so this is x equals 4. And now let's see, so now we see that on the outer bounds of integration, where we're doing dy, we've got y equals 0 to y equals 2. So I go back and say, okay, so y equals 0 to y equals 2. And it turns out that's right exactly here. Okay, so the way this integral was set up, it was set up to be, let's see, using my usual color scheme, it was going from green to red, picking up these slices here. These are horizontal slices because we were doing the dx integration first. Okay, so now I have understood the region. Region is decoded. Okay, and now I'm going to figure out how to set it up the other way. So I have this region, and now I want to think about starting on the bottom and ending on the top, so that I have a bunch of vertical slices like this, where I'm integrating dy first. Okay, so that means I'm going to go from this bottom one right here, which is y equals 0. That was not too hard to figure out. And then I need to think about this top bound. So what did we have before? We got this by looking at x equals y squared. So now, I guess, in order to solve that for y, this is going to be y equals square root of x. And it's the positive square root, because the negative square root would be down here, and we don't want that. Okay, so my upper one here is y equals root x. And then I'm going to be picking up these slices from my very first one here, where I just get that single point at x equals 0. And I end here at x equals 4. Okay. Notice I'm doing this all from the diagram, all from my picture, all using the geometry and so on and so forth. People will be tempted to make shortcuts by just trying to solve some of these variables in terms of other variables and come up with some quickie trick. Resist the temptation. Do not go to the dark side. It ends only in tears. Honest. Trust me. If there was a nice way of doing it, we would have told you. We're not here to make you suffer. I mean, mostly not. So let's see. So now we can equivalently set up the integral as, okay, so same integrand, right? Nothing changes with the integrand whenever you change the order of integration. But now let's see, we're going to be doing dy first, and we're going to go from 0 up to root x. And then we're going to do dx, and x is going to go from 0 to 4. Okay, and so let's see. So this guy we can actually evaluate pretty readily. I know nobody wants to see that square root popping up, but it turns out to be just the thing that we need to make this happen. So this is going to be, let's see, x squared over 2 cosine x squared dx, and now we can do u equals x squared du equals 2x dx, change of variables. That u substitution gives us the new integral 1/4 cosine u du, and with the new bounds of integration, that would be from 0 to 4 squared, which is 16. And we can evaluate that as, so 1/4, and the antiderivative of cosine is sine, 0 to 16, and we get 1/4 sine of 16. So who knows what that is? Its argument's not a multiple of pi, integer multiple of pi, so I can't tell you, punch it in on your calculator or something. But hey, not too bad to integrate, right? Way better than the impossibility that we were dealt with in the beginning.